Good morning, everyone. This is Shekoff, and we're here to talk about the basics of electricity. While we're waiting for other participants to join, I'm going to run a very basic clip, and we're going to wait for others to join, and then we're going to kick it off.
When you're in the dark and you want to see, you need
electricity, electricity.
Flip that switch and what do you get? You get
electricity, electricity.
Every room can now be lit with just
electricity, electricity.
Where do you think it all comes from, this powerful
electricity, electricity?
Through high wires to here it comes, they're bringing
electricity, electricity.
Every building must be wired to use it
electricity, electricity.
Power plants most all use fire to make it
electricity, electricity.
Burning fuel and using steam, they generate
electricity, electricity.
Turn that generator by any means, you're making
electricity, electricity.
A generator is a machine that contains a powerful magnet that creates a magnetic field. When wires are rotated rapidly through this field, then a current of electricity is produced. Now, if we only had a superhero who could stand here and turn the generator real fast, then we wouldn't need to burn so much fuel to make
electricity.
Benjamin Franklin flying his kite was searching for
electricity, electricity.
He knew that it had something to do with light, and it's all
electricity, electricity.
Rubbing a comb with wool or fur will give you a charge of static electricity. Stroking a cat to make it purr, you're building up static electricity.
Electricity.
Electricity at rest is called static electricity. Like in the winter, wearing a heavy coat, you get a shock off the doorknob, or you scrape across the carpet and sneak up on your very best friend and zap him on the ear with the shock of
electricity.
Current flowing to and fro makes a circuit of
electricity, electricity.
Voltage is the pressure that makes it go. It's pushing
electricity, electricity.
Watts will tell you just how much you'll be using
electricity, electricity.
Powerful stuff, so watch that plug. It's potent.
Electricity, electricity. Electricity, electricity.
So good morning again, and thanks for joining the basics of electricity class. I'm going to rewind the slide a little bit to go back to the introductory slide. My name is Shekoff, and I have a background in IT, software, hardware, computers, going back to the early days when computers were very expensive, took up a lot of space, not just on your desk, but in your room and altogether. And as computers became more and more advanced, and as more technology came out with my love for outdoors, going into the various alternative energy research was a lot of fun for me, and I'm doing that still. So I do a lot of my electrical work at home by myself with the help of YouTube from time to time. Also do a lot of off-grid solar systems. We've done a couple for boats that we have. We've done one for a friend of ours, Dan from Return to Nature, and we've done a few on our library, community libraries, so that adults can charge their phones while kids are browsing through books. So kind of a win-win for everybody. So I think kind of housekeeping basics. Everybody's basically mute. We're going to have a Q&A session afterwards. And there's going to be one quick exercise, which is going to be, in which case you can actually turn on some of your microphones and video cameras, and we can take a moment and look at the exercise results. So with that said, let's go and go through a couple of slides that we have for you. So kind of a rhetorical question, open question for everybody. Do you know what electricity is? And I think most people think of electricity as something that powers most of our life, something that gives us light, something that gives us ability to charge our phones, something that gives us an ability to have fun, watch TV and things like that. And in some cases, most of you now know, they even power up our cars. So what is electricity? Electricity really is an electric current. And this is a very, very simplified picture, but electrons, the little tiny electrons running along the wire is basically an electricity. Now, of course, wires can be different size and different shape. They could be very thick, those wires that you see running overhead as you drive along the road. And they could be tiny little wires that you can barely see inside your phones or inside your computers. So you may want to ask, well, now that you know that electricity is electrons running along the wire, what are electrons? And that would be a great question. So electrons are little particles that surround the nucleus of an atom. And we're going to dive a little bit more into chemical and physical compositions perhaps, but all we need to know for the benefits of this class is that they're atoms, tiny particles that make up basically everything that we know, including us. So the air around us, the walls around us, the glass, the cars, the food, and our bodies, they are all made out of atoms. And those atoms have nucleus, which is like a center of it. And I'm going to circle with my mouse over here. This is the nucleus of an atom that has protons and neutrons. And around them, at a very, very high speed, fly, like these, electrons. So these electrons, because they're not part of the atom center, they are welcome to be shared with other atoms. And by having those electrons travel in a specific destination, we can actually create electrical current. So again, very quick recap. These atoms, which are very, very tiny particles, they all have electrons that travel around the nucleus. And those electrons, when they travel on a wire, is what gives us the electricity. All right, so here is a very overwhelming picture. That's a sample electrical diagram. If you look very closely, you can actually see that this is kind of a small little electric car or a golf cart probably. This diagram shows wires in different colors and shows different electrical components, lights, fuses, switches, and everything is labeled, everything has numbers, everything has colors. This is an example of an electrical diagram, so you can figure out how things are connected. We're obviously not going to go into the details of what this diagram do exactly, but that's just a good good picture to show you. Whenever you look at the electrical diagram, it will look something like this, and you'll see things that are switches, things that are lights, things that look like triangles, and things that look like semicircles. We'll talk about a little bit about that in this class. So moving right along, I think most of the questions people ask, well, how do we measure the electricity? We know what it is, right? It's electrons. And so how do we measure it? Well, let's imagine electricity as plumbing. right? Everybody knows plumbing. Everybody knows water flowing through pipes. So if that's the case, then the speed of the current is called voltage. And everybody, I'm sure, heard that, you know, it's 110 volts, or it's 200 volts, or it's 12 volts. So, or very commonly known, 1.5 volts, which is the voltage of a little batteries that we put in our devices around us, that surround us. The next item we want to know is the amount of electricity moved per unit of time, and that's called amperage. Now, this is something that most people are not familiar with. They've probably seen it, they probably heard it, but have no idea what it is. So what it is really is the amperage is the size of a pipe. So again, we talked about water traveling through a pipe. If the pipe is 4 inches in diameter, you can only move so much water through it. If the pipe is 1 inch in diameter, you can move a lot less water through it. And if the pipe is 1 foot in diameter, you obviously can move a lot more water to it, even if the speed of the current is the same, right? So if water travels at 5 miles an hour through a pipe that's 4 inches long, and water traveling through a pipe that's 8 inches long, while the speed is the same, the amount of water will obviously be different because of the size of the pipe. And that brings us to the last item that we're going to discuss as part of this class, and that is the wattage, the total amount of electricity that we need. So the wattage is really how many gallons of water flowed through the pipe over a time period. So everybody, I'm sure, know what wattage is or heard what wattage is. The very simple explanation is you have an electrical bulb, and the electrical bulb is rated in watts. So when you go by it, it says, oh, this bulb is 40 watts, this is 60 watts, this is 100 watts. So to most of us, it's all about how bright it will shine. But now, hopefully after the end of this class, you'll understand why exactly is the wattage, difference in wattage will make the bulb shine brighter or dimmer. So moving right along and kind of recapping, voltage is the speed with which electricity travels. Amperage is the size or amount of it moved per unit of time. And combination of voltage and amperage is wattage. So with that said, let's look at, do a quick exercise. Now, quick exercise, I'm going to show you a couple of labels, and together we're going to identify what are the parameters of electrical components that we're looking at. So the first one is something that I'm sure a lot of you've seen, is an adapter by Apple. Right? This is one of the iPads or an Apple Mac adapters. And so on the bottom of it, and in the very similar adapters that you use in your daily life, you'll see something like this. You'll see a bunch of information, bunch of icons, and among that, you will see something like input, 100-240V, approximately 0.5A, 50-60HZ, and then it says output. So let's take a look at this label and figure out what it tells us. So this is an adapter. So obviously this is not an actual device that does something. It only takes the electricity from one form and converts it into another form. That's why we have an input right here, and we have an output right there. So the input is 110 to 240 V for volt. So that's your outlet in the US or in Europe. So a lot of European outlets are 240 volts. We'll talk about that a little later. 0.5 A stands for amps. So that's something that we've seen earlier on the slide. How do we measure the amount? So half an amp is what this device inputs. And 50-60 Hz, now the Hz stands for hertz or frequency, is something that we'll talk about a little later when we talk about different types of electricity. So again, it's 110 volt or 100 to 240 volt, half an amp input. So these two prongs right here is what they grab from your house outlet. Now the output is listed right here. Now the output is 5.2 volt, and you'll see this little line with dashes underneath it, well, that tells us that this is a specific type of current, which we'll talk about in a moment, and it's drawing 2.4 A or amp. Now remember the previous slide, so we talked about volts and amperage and wattage. So if we take the volts, 5.2 times 2.4 amp, we'll get 12 W or 12 watts, which is what they conveniently listed on this device. So for the purpose of our exercise, this particular adapter consumes 12 watts of electricity at 5.2 volts. Okay? And we can come back during Q&A later if anybody wants to ask questions on this. Another example, slightly different, is a label from probably a household appliance. If you read closely, it says fully automated washing machine, so that does qualify as an appliance. So here it's not as easy to understand the power consumption or the electrical characteristics of it. So you have to scan this a little closer, and as you start scanning, you'll see things like serial number, a bunch of labels, product code. Somewhere here you'll see 120V. So that 120V stands for 120 volts. 60Hz stands for 60 hertz. That's the frequency. We'll talk about that in a moment. And 10A stands for 10 amp. So very quick question for those of you who are on the call, or for those of you who are watching this as a recording. I'm going to pause for a second and let you do the math. So if you're running on 120 volts at 10 amp, figure out what the total wattage of this device is, of this fully automated washing machine. So 120 volts, 10 amp. Frequency is not very important at the moment. So if you need a calculator, it's fine. If you don't need a calculator, that's fine too. So the answer is, we'll take the voltage multiplied by amperage, and we'll get our wattage. So 120 volts times 10 amp will get 1200 watts, or if we do this in kilowatts, 1.2 kilowatts. So remember, 1 kilowatt is 1,000 watts. Okay? To simplify and get rid of a whole bunch of zeros. So let's move along. So this exercise, we didn't see the wattage listed. It was probably listed somewhere else, but not on this label. But we were able to figure it out. So generally, it's very simple to figure out voltage, amperage, and wattage using this particular formula. So voltage times amperage equals wattage. If you guys know about math, hopefully a little bit, you can figure out that voltage is really wattage divided by amperage. And then amperage is wattage divided by voltage. So it's very, very simple. Now this is obviously oversimplified for the basics class. And for most of us in our daily lives, we probably do not need to know much beyond this. But in case you do want to know what other things we can measure, here's another very cool diagram. And this one brings a couple of more things into the perspective, such as resistance. So the resistance is something that a material out of which the wire is made can either help electricity flow or can prohibit it from flowing well. So some materials like copper and iron are very good. They conduct electricity very nicely. But others like rubber, perhaps, or plastic, they don't really conduct electricity. So they would actually be very prohibitive to electricity flowing in a particular direction. So, but again, when you're calculating advanced formulas on how much power you need to power a device, it's good to bring the resistance into the equation. So again, these formulas are for more advanced, and they look kind of nice for a slide to keep in mind. Power here, that's our wattage, voltage. Current, that's our A, amperage, and resistance. Again, scientifically, these are the symbols that we use, P, V, I, and R. But for our daily lives, we use these. All right, moving right along. So we talked about a couple of different types of currents early on. We saw that 120 volts, we saw 5.2 volts. So to really simplify it, we have two types of current. we have a direct current. So you see this picture on the top. This is where the electrons flow in one direction all the time. We have also alternating current. And just like the name suggests, they can flow in both directions. They can go one way along the wire, and then they can change and go another way along the wire. So here's a little illustration that shows you how they differ. The direct current on the left is usually associated with batteries. And you know that most batteries have a positive and a negative, plus and minus. So here we have a picture of the battery and the current flowing one direction nonstop. On the right-hand side, we have AC current, alternating current. And usually it's depicted by a slightly different image. And here we can see that every so often, the direction reverses, just like it did now. So here it flows this direction, now it's flowing to the left. So for the alternating current, you can see that it can travel in one direction towards a positive, and then it travels towards a negative, positive and negative. Now, it's important for alternating current only to know the frequency. How frequently does it change the polarity or direction? And so here's another diagram that gives you a little better understanding of how it changes. You can see that every time this little dot crosses the green line, the horizontal line, the current, the little lights, little dots, change direction. And so remember we were talking about 50 or 60 hertz frequency? Well, this is exactly what it is. So the 50 hertz is the frequency that's usually used in Europe, and that means that they are changing current a little less frequently. 60 hertz is the American standard, and that means that we're changing direction the electrons flow more frequently, and by about 15–20%. Okay. So we're going to do a quick exercise. And for those of you who are watching this in the recording, I will pause, or you should pause the recording, and after you get the instructions, go ahead and do the exercise and then resume the recording. So the exercise is very simple. In a moment, I'm going to unmute the lines. And those of you on the call, I'll give you a chance to kind of see if you can figure out one example of a DC and one example of an AC current device. And perhaps some of you guys can explain why you think this is a DC device or an AC device. So while you guys are thinking about it, I'm going to go ahead and unmute the lines. And if you want, you can turn on your videos. To turn on your video, you have icons on your devices, right-hand side, left-hand side. I'm going to go ahead and start my video as well. And let's see. Anyone wants to give examples of, let's start with a DC current or a DC device? Anybody? All right, so I'll name the first one. Very easy. A device that uses DC current is a car. Why is a car? Well, the car has a battery. The car is usually not plugged into the household outlet because it needs to travel great distance. So a battery, we all know about it, it's somewhere under the hood usually, has a plus and a minus signs, and therefore it's a DC device. All right, anyone else has examples of DC devices?
Just turn on your speaker and you can give us your answer. Yes, Ben?
Helicopter?
All right, well, probably a good answer because helicopter probably has a battery on it that makes it possible to start up the motor. How about something that you use a lot in your daily lives? Go ahead.
Computer?
That's good. Now, what kind of computer?
Mm,
What kind of computer do you have then?
right now I'm using a monitor.
Okay, so you have a monitor and you have a desktop somewhere, right?
Yep.
Is that desktop plugged into your outlet?
Yeah.
Okay. Does your computer have a battery? Is it a laptop computer?
Yes, I guess. Yeah.
So if it's a laptop computer, it's an example of both DC and AC current device, because while you plugged into the wall, your computer uses the AC current, right? And when you unplug and you're using only the battery, you are using the DC current, because the batteries usually do not have alternating currents. What else? Something small, something that you guys all like to have, and you usually buy one every year or two. Yes?
A phone?
Right. So a phone is probably another good example of a DC device, and that's because it has a...
Battery?
That's right. Good job, man.
Duh.
All right. So how about more examples of AC currents? And again, this should be easy enough once you understand that they really have to be plugged into the outlet. Okay. So I think a good example would be the washing machine that we saw a label of a little earlier. And maybe a TV.
A blender.
A blender. Thanks, Olga. So, so you guys understand. So DC current device is something that usually runs off a battery. Could be a big battery, could be a small battery. An AC current device is something that's usually plugged into a grid, electrical grid that starts somewhere with a power company and ends in your house with an outlet. All right, so now we're going to go in through a couple of different items. If you want to mute your audio, so easy, you can talk at home. So a couple of things. So electricity by itself is harmless. When you work with it, this is where potentially some issues may come up. So safety is very, very important when you're working with electricity. So first and foremost, you never experiment with electricity from your wall outlet. So the AC current is usually much stronger than a DC current. And any experiments you do with it, if there's a problem, the consequences are substantially greater. So you don't want to experiment with anything that has to do with outlets in your house. Secondary, batteries that store electricity can harm you. You know, you don't think of them as much, you know, AA, AAA battery, something that you put in your remotes, you know, every day, a battery for your phone. Those are tiny, right? They're very small. Another, a good example of how deadly even they could become, or how dangerous they can become, is the Samsung Galaxy Note 7, a device that a lot of you are familiar with. The device is actually removed and banned from all air travel. So when you travel, you cannot bring that device with you on board because it has a defective battery built. And what happened with some of those devices is the batteries heated up and caught on fire. So that's another good example that you should never really take your phone with you to bed, because even though your phone never has a history of fire, you don't want it to heat up, you don't want it to have any potential harm. So always store them in a secure place where it's not close to you. Another good thing to know about electricity is something called grounding. Okay, so the grounding is when you have connection to the ground, to earth. That's the best place for electrons to escape. So whenever you have an electrical current that goes bad, an accident or a wire that's exposed, if you are grounded, or if your device is grounded, all the potentially harmful electrons will simply go along that grounding wire into the ground, and no harm will be done to you. One other thing is important whenever you have experiments. I'm sure in school you're going to have some experiments with electricity. It's always a good idea to wear rubber gloves and have plastic glasses. You know, in case there's a spark, in case there is something, even low voltage, even from a battery, you should be protected, your hands and your eyes. And finally, respect electricity. While it gives us lots and lots of great things, it's something that can potentially cause harm. So be mindful of that. All right, and then lastly, we'll have some fun with electricity. We'll talk about fun facts, and then afterwards we'll talk about Q&A. We'll have some questions that you guys can ask. So fun things. Electricity travels at 6,696,000 miles per hour. So that's kind of fast. That's basically the speed of light. Static electricity, you've all seen it, right? Sometimes you take your hat off and your hair stands up. That's called static electricity. So this means that this electricity is not really traveling through a wire, right? Your hair is not wire. It's just building up around you, around your hair, around your skin, or around wool objects, perhaps. You know, so it stays there and it doesn't do anything until you sometimes touch a metal object or something else or another person, and all of a sudden you'll see electric shock. Like it's almost like you see a little spark. That's a mini lightning, right? So that's static electricity, something that was in your hair or something that was not moving, all of a sudden found a path, said, oh, I see a way out. I'm going to go there. And when it does, it creates a mini lightning or an electric shock. Another interesting fact is the first power plant opened in 1882 in New York City. And if you guys want to look it up later on, I'm sure you'll find it very interesting and probably not very difficult about the person who opened it. Hopefully you'll find the answer very quick. And then last fun fact is that the lightning bolt, something that we see in the sky during rain or thunderstorms, can reach 10 million volts. There's something to think about it. The outlets in which our computers are plugged in, it's 110 volts. Now this is something a million times greater. Okay, and so before we go into a Q&A session, just wanted to give an update on the next class, which we'll have in a couple of weeks. We're going to use some of the knowledge that we've gained here, and we'll talk about applying solar energy for domestic needs. Domestic needs could be charging your phones while you're outdoors, or living in your car, you know, while you're traveling, you know, across the country without having to plug in or recharge. And we'll talk about how the solar light becomes electricity. We'll talk about the batteries, the battery types, and we'll even look at some pictures on how the electrical setups can be done on your house, your car, or your boat. And with that said, we'll jump up to Q&A session. And let's make sure that your microphones are unmuted. If you want to ask a question, you can turn on your videos. You can turn on your cameras. And if you guys have questions, go ahead. Well, that was something very fast. Hopefully that was a question. I kind of have a question. Just wanted to know if everyone who joined the call, if they found the information useful, if they were able to follow along. If you want, you can speak. If you want, you can add something to a chat. And if you'd like to know a little bit more about different topics related to about electricity. Okay. Okay. So
Alex, maybe you can, in chat, you can type our email address in case if anyone has questions later on.
Sure, it's a great idea. So if you have a question related to electricity, if you have a question about this class or something that we reviewed in the class, if you have questions about something that you want us to review in future class, you can send us a quick email at info@antinanco.org. I'm going to post the email into the chat, so you can always take a look. If you want, you can copy and paste that. Anything else? Any other questions? Any other comments? And if not, well, thank you everyone for joining. Looks like we had a lot of people join in. And hopefully this information was very useful, or at least fun and informative. And if you want to dial in, stay tuned for information about our next class.
Can we just give a quick homework to everyone? Guys, if you have a few minutes sometime this weekend, why don't you calculate based on the formula that Alex gave you? Just grab any device that you have around you and do your calculations.
That's a great idea. Another thing that you can do, kind of a next step from what Olga was mentioning, is figure out how much electricity do you consume in your home. That's going to be a little challenging, but that will give you a good idea about how much power you use, how much power you waste. Yes, we all waste electricity. It comes very easily into our homes, and we usually sometimes leave the lights on. Depending on types of lights you have, you may have different usage. So I think that's a great exercise. Go around your house, look at your electrical devices. Again, make sure that you do not go into the outlets. You do not touch the outlets, and just look at the devices themselves. And if the device has a label that's hidden and you need to go open the cover or something like that, I think that's a little too advanced, so don't do that. Usually you'd want to unplug that appliance first and then start looking at it. You know, something basic, you know, look at your electronics, look at something like your refrigerator. You do not need to unplug your refrigerator to see some of the information about its electrical usage. All right, and with that said, everyone have a great afternoon, have a great weekend, and we'll talk to you next time.